Okay, first question, why sample? I think the obvious thing, first of all, is because the population is too large. Unless you're the government doing the census, populations are too large to go to every single person in that population. So in this case, you sample. Now, there are some examples other than the census that don't sample. One you'll be familiar with is the National Student Survey. That takes every single student who's registered and sends out a questionnaire to them, asks them to fill it in. Of course, they don't all do that. Response rate is relatively low, but nevertheless, it is every single person in the population who is being targeted. But more generally, more commonly, we usually sample because it's much cheaper to do that, to find a subgroup and then go to them and ask them the questions. Other reasons are because the population is too dispersed to find. We don't quite know how to contact them or find them or whatever. We can define them in some way, but we don't know how to get hold of them. For years I've used this example of swimming clubs because I don't know of any list of swimming clubs. How do you find out who are the members of the swimming clubs? There is no kind of list you can just simply send to every single swimming club member. But I'm sure there must be clubs, there must be membership lists, but finding them is an issue, and you have to use other kind of techniques to find them. I'll be talking about this later on, but some kind of cluster sampling might be the way to go here to find subgroups and just pick certain clubs and sample them only and so on. Third reason, and this is another very important reason, is that we sample to do things quickly. And that's particularly an issue in things like opinion polls, where it matters that you get the results in just a couple of days because it's timely, it has to be before the elections takes place. You don't want the results of the opinion polls after the election's taken place. Nobody's interested then. They want to know before the election. So that's why it's important to do it quickly. And they use specific sampling techniques to enable them to do things quickly and get results out and get them published, of course. But more commonly, as I said, the most common simple survey is a kind of snapshot. And you don't want a snapshot that's telling you how things were 2 or 3 years ago. You want a snapshot to be at least reasonably timely within the next kind of few months of it actually happening. Because you may want to take some action based on it. You want to change policy or do something on the basis of those results. So you don't want something that's out of date. So getting things done quickly is another reason why you only look to a sample rather than the whole population. It's just easier to do it fast. Okay, this last point here, the key to sampling. It's an often repeated point, and it comes up in all kinds of different ways. And if you read the textbook, sometimes you watch things on TV. I've actually seen some pollsters on TV talk about this. Sampling, the key point to sampling is to get a representative sample. And a common metaphor here is the blood sample. If you take a sample of blood, a couple of cc's of blood, the assumption is that that blood is typical of all the blood in the body. And in general, that's true. There may be 1 or 2 odd occasions where it isn't. I can't quite imagine how. It's quite difficult to think of it how. I suppose venous blood's different from arterial blood and so on, but but apart from that, the mixture of things in the blood is good. And that's the important point. Everything's mixed up in the blood, and taking just a couple of cc's is typical of the whole body. So taking a blood sample is a good technique for telling you what all the blood is like. If only humans were the same, if only people were the same, if you take a sample of people, you have to be very careful how you do it. It's so easy to get a sample of people which is not typical of the whole population. So the key to sampling techniques is making sure, as far as you possibly can, that when you do the sample, it is typical. And we use a whole set of techniques for that, but the most common one is some kind of random number approach. So we pick, using random numbers or random techniques, we pick a sample, and we hope that that makes sure that there are no biases in there, that we are picking relatively typical. We can't guarantee it, of course. A random number approach doesn't guarantee it's typical, but it's more likely to be typical than any other approach. If it involves human choice, if in some way you are choosing things, or a person is involved in picking the sample, then it's not likely to be representative. It's likely to be biased in some way. And so that's a less appropriate technique. We can't always avoid that, but we have to be aware of the fact that it is jeopardizing the representativeness of the sample. So that's the key issue. Another issue is how big a sample. I mean, as I said, the sample is not the whole population, it's not 100%. So what's a good sample? Is it 10%, 5%, 90%, or whatever? Well, here's some of the criteria that you have to think about. Usually, in big populations, less than 10% is fine. So if we're talking about populations of hundreds of thousands, millions of people, then less than 10% is certainly okay. I mean, in the case of Kirtlees, as I said, 250,000 people, 10% sample would be 25,000. That's certainly by far and away enough people, plenty of people in that sample. More commonly, you have to start thinking in terms of sampling errors. When you take a sample from a population, particularly if you're using random numbers to do so, there is always a possibility of a sampling error. That it's just simply through some kind of bad luck, you get a population that is not actually perfectly typical. And you never can guarantee that. And on some occasions, if you're doing it using random numbers, on some occasions it'll be less typical than other occasions. On the whole, it will be typical over a period. If you do the same sampling strategy year after year after year, then in the long term, it will be typical. But some years it may not be. It'll have an error called a sampling error in it. And using some calculations, you can work out how big a sample you need to minimize that sampling error. Now that depends upon how much variation there is in the population. So if there's a high variation in the population, you need a bigger sample. And it depends on obviously the population itself and the sample size you take. Generally speaking, things like about 2,000 from a large population tend to be acceptable. In other words, the sampling error is low enough, usually in the few percent area, that we don't worry too much about it. And we've got enough people in the sample to get some reasonably reliable results, provided we've done it properly, provided we've done the sampling strategy properly. Now you might think that looks like a big number. If we're doing properly designed studies done by government, by universities, done by commercial companies and so on, then they will be thinking in these kind of numbers, 2,000, 3,000, 4,000, 5,000, very common numbers used in surveys. If you're doing it in a student project, an undergraduate project or a postgraduate project, then these are huge numbers. Getting hold of this number of people, unless you're doing it through the web, is quite difficult to do. So there's often a compromise, and that's, I suppose that's number 4 actually I've gone on to now. Number 4, small enough to carry out with your valuable resources, and that's often, in the end, in student projects, that's what it comes down to. So, if you're doing an undergraduate dissertation, then normally 100, 200 is acceptable. It's not perfect. It does compromise things. The other thing to think about too is subsets. You may have 2,000 in your sample, but if you've got some kind of variable that is important in your study that breaks people down into 10 subgroups, then each subgroup may only have a couple of hundred in it, or maybe even less than that, because subgroups may not be the same size. Maybe only 50 people in a subgroup, for example. Now, if you want to know about that subgroup, you've got to increase the sample size of that subgroup, if not the whole sample, so you've got enough people in there for them to minimize the sampling error. So the sampling error issue is not just the whole sample, but perhaps with the subgroups as well, and you have to worry about having enough there. If you're doing some statistical tests and things like that, you often need large enough numbers as well to do statistical tests on them. That's what the kind of tables idea comes from. Okay, so in the end, sample size can be a matter of compromise. That's all the time you've got, the resources you've got, etc. to do it. But think about other issues like the sampling error and the overall population size. Let me just introduce this distinction in sampling approaches between probability, using the random numbers approach I mentioned already, and non-probability approaches. The probability approach is, if you like, is the gold standard. It's the one that we all try to use. It's the one which others are measured against, in a sense. It's the best way we have of making sure our sample is representative. It's using some kind of probability sampling, some kind of random number techniques. So rather than any person choosing, The choosing is done on the basis of random numbers, and that can be generated on a computer, or it can be done by tossing coins or whatever. But the key point here is that every person in the sample, and the reason it's called probability, every person in the sample has a known chance of being included. In many cases it's the same chance, but not always, but certainly a known chance of being included. So we can say every person, whether they're chosen or not, has an X% chance of being chosen in this study. And the other important point is once we've done that, from that sample you can then make various statistical inferences. So you can say on the basis of statistics, this sample tells us we've got this many people doing this, so on average we expect in the population to have this many people doing it. So it's very good for making predictions, if you like, about the whole population, and therefore it's the kind of thing that policymakers and planners and so on like, because it gives them really solid information about the population in general. So the gold standard, probability sampling, and I'm going to talk a lot more after the break about different ways of doing that, of creating those kinds of samples. But we can't always do that. It's not always possible to do probability sampling. There are certain things you need in order to carry out probability sampling approaches. Time is one of them, resources another one, the right kind of populations and information about those populations are important. If you haven't got that, you may have to resort to non-probability sampling. And the point about non-probability sampling is it involves some kind of human judgment to pick the people you're working with in your sample. The sample may be representative. We don't know. That's the important point. It may be representative. And in fact, there has been some research that shows that non-probability samples done using certain techniques can give us samples that are pretty good, pretty much close to what we would get using random number or probability approaches. But in many cases, we can't tell for certain, and in many cases that doesn't apply either. They're not using those techniques, and so the sample is not representative. And we have to be aware of that, and that of course limits the degree to which we can generalise from our sample to a wider population. But sometimes we have no choice, and I'll mention some of those at the end of the session today. Different kinds of issues to do with probability sampling. The first thing, and this is an important issue for some of the things you've been looking at, some of the problems you've been having, I suspect, with getting good samples from the examples you've been looking at, are the need for a sampling frame. Sampling frame is a list of people from which you can draw your sample. And if you're doing it using probability or random number techniques, you need a list to do that in some way. At its most basic, it's a list of everyone in the population. And you pick from those. Now there are problems with that. Sometimes the list may be inaccurate in various ways, like maybe missing categories. If you're doing a survey of students in the university here, for example, you might miss some students. Students who are registered only as kind of occasional students, or just students registered for one module but not for a course. I mean, a couple of years ago I did a one module German course. I wasn't actually registered on a degree as such, just taking a module. Now, am I a student or am I not a student? I got a student card actually, so I think I should have been a student in that sample, but it may not have been picked up when you get the official list of students. It might be all the courses that they've done. So you're missing out some categories of students. You need to decide whether they should be in or not. There can be inaccuracies. Obviously, lists aren't always perfect. People who turn up late or get the names wrong or whatever, the admin people get the names wrong. We're not quite sure who they are. Maybe appear twice for some reason because the first name and surname are swapped round and they appear as two people. All sorts of things can go wrong with these systems, of course. Sampling frame can be in the wrong units. That's something which I think one of the questions kind of prompts you on. You may not realise that, but it's hidden in the question. You need to have the list in the right units. And if you're wanting to have families, you've got to have a list of families, not a list of people. If you want people, you're going to have a list of people, not families, and so on. Those kind of things, or households and things like that. Sometimes you need information for stratification. I'll come back to that in a moment. I'll talk about stratification issues, but it's a way of reducing the sampling error, essentially, to getting a more accurate sample, if you like. You need to know a bit about the population. If you don't have that, you can't do stratification. And you need some kind of list of contacts sometimes. You need to know how to get hold of it. If you're going to send a survey to people in the post, you need an address to send it to. You need to have some way of getting hold of the individuals. So these are all problems that can occur here. Somewhere, I'm sure I should have said it here. Wrong units, stratification. I think probably comes under number one. A most common issue here is people being left off the list because they've gone away or they've died or whatever. So mortality issues can be a problem with these lists. Particularly lists of house, people in households can move house and it's not up to date, effectively. Okay, well, I've already hinted at this by talking about stratification. There are different kinds of probability sampling. And here's the list of the ones I'm going to be talking about. These are the most common ones. Simple random sampling, the one you're probably familiar with, you just simply take a sample using random numbers simply from the population. And what you need for that is a list, the sampling frame to take the sample from. That's not always convenient, so that we sometimes do it systematically or quasi-random. And I'll tell you how that's done. And that probably is the most common way of taking samples, is the systematic approach. We can improve the samples, we can reduce the sampling error using stratification, so that's the third approach. And we can then start to combine different kinds of stages. If we haven't got sampling frame for the whole population, we might have sampling frames for subpopulations. So we can do a kind of mixed sampling approach called a multistage. And then cluster sampling is a form of multistage sampling, which we'll talk about. Let me explain those in a bit more detail. The simple random sampling is where every member has an equal probability of selection. Epson is the acronym sometimes used here. It's not much used these days, that term, but an equal chance of selection. Very simple. And you select by some kind of random number process. It can be a lottery, tossing coins, lists of random numbers. I mean, old textbooks used to have lists of random numbers in the back that you could use. You just kind of close your eyes and point somewhere on the page, and that's where you start. And then you just lead off the numbers to get the numbers you need. These days, of course, it's computer generated usually. Excel, for example, has a reasonably good function inside it to generate random numbers if you need them. And that works pretty well. It's pretty instantaneous as well. So that's the main way people do it these days. So you have a list, that's your sampling frame. You put numbers, you number them, 1, 2, 3, 4, 5, 6, 7, 8, etc., all the way to wherever it is, 250,000 at the end. And then you generate your numbers, which will be, in that case, between 1 and 250,000. And then you pick those people from that sample. They're the ones that you're in your sample. It's a very simple method. Simple, but very, very tedious if you've got a large population. Imagine going through 250,000 people, giving them all a number, and then having to select 2,000 or 3,000 from them using random numbers. It can be rather tedious. So that's why we often use the systematic or quasi-random approach. It's statistically just as good, where there's no human choice involved, so it is still, in that sense, a good sample. But it's just slightly less kind of variation in the samples that we can actually get. As I say, simple random sampling is very inconvenient, particularly with large populations where your sampling frame's enormous. So what you tend to do here is we don't number them all, you just start from a certain position in the list and then pick every nth person, or actually I've said rth person, sorry, every rth person on the list through that. So if you're taking a 5% sample from a population of 2,000 people, i.e. you're getting a sample of 100, 5% of 2,000 is 100, then R becomes big N over little n, that's 2,000 over 100 is 20, so every 20th person. Another way of thinking of it is 5% is a 20th, so that's what you want, 1 in 20 of the people chosen. So you do a little bit of coin tossing at the beginning to get your first number, or go to Excel and get a random number between 1 and 20 to pick your first person. Let's say that's, what do I say on here, 13. That's the number you've chosen at random. And then you do every 20th person from then onwards. So you pick number 13, 13 plus 20, 13 plus 20 again, plus 20 again, and so on all the way through up to 1,993. So actually, provided you've got the list, you don't need to number them, you just simply count through in that way. And that gives you a very good sample. It's random, certainly, there's no human bias involved in it. Slightly fewer combinations than you would otherwise get, but that's not a big issue. The only real issue here is if your listing is instructed in some way. Imagine your list is one male, one female, one male, one female, one male, one female, all the way through. Doing it this way, you're going to get a sample that's either all male or all female, depending where you start. So you've got to worry a bit about that if the lists are structured. But that's a relatively minor problem. Very few lists are structured in any way like that. It's going to upset this kind of approach. But just one thing to worry about there. The idea is you want 5%, so that's 1 in 20 you're going to pick. Okay, so you have to start somewhere. The first 20, you've got to, you're going to pick somebody from the first 20 people, but you've got to pick somewhere in that list. So you get a random number from 1 to 20. And I just happened to have chosen 13 when I did it. But you toss a coin to do it, or a number of times to get the number, or you can go to Excel and get a random number from it. But you have to start with some number between 1 and 20. That's your first person to pick. So you then count down the list, 1, 2, 3, 4, 5, down to 13, and then that's the person you pick, number 13. And then you count 20 more people down the list to give you number 33, and you pick that person. Another 20 down the list, number 53, you pick that person, and so on, all the way through. So you've then picked 1/20th of the people, i.e. 5%, to give your sample of 100. And that's what I'm indicating here. Okay. One of the problems with this kind of sampling, this kind of systematic or even simple random sampling, is you can end up with samples that are quite disparate and sometimes actually not typical. I mean, being random numbers, there's always a possibility of it being untypical to a certain degree. I mean, less likely that the more untypical is less likely, but nevertheless there is still a probability there. So what we can do is use stratification to try to reduce that sampling error, to reduce the chance that the sample we get is a bit odd in some way. And you do that by dividing the population into strata. That's what this little picture at the top indicates, the kind of strata in the soil, different kinds of depths and different kinds of widths of strata as you go through the bedrock. And what we do is effectively bore a hole through that, and the hole we're boring through it is in the same proportions as the rock itself. So this is a hole, if you like, bored through side view of the rock. And each stratum appears in the same proportion as in the rock bed itself. And of course, in the case of a human population, what we make sure is that each group within the stratum is in the same proportion in our sample as it is in the population in general. Now, of course, to do that, you need information about the population. And I mentioned this earlier on when I was talking about sampling frames, that you need that information. If you haven't got it, you can't do this. But if you've got some information, for example, you can often get stuff from a previous census. That's good enough. Stuff that may be a few years old is good enough to do a stratification on. So you can use that data to stratify your sample and say we need X% of this kind, X% of that kind, and so on.
So if I wanted to do something about end-of-life care for people who are in receipt of fast-track funding from the NHS, and I wanted to, that would be a good thing because there's lots of different people involved in the care of that person, including that person.
I mean, typical things here, provided you have the information to do it, typical things here would be gender. That would be one thing. Are they male, are they female? And you would make sure that your sample was in the same population, same proportion rather, as the population. So if we talk about older people here, the likelihood is quite a large number of female. There might be, 57% female and 43% male, in which case your sample will be in that same proportion. Not the whole population, but in the same proportion. And you might want to have certain diseases. You might have cancer and heart disease and so on. And again, the same proportions as in the population you're looking at, your target population. So you might be, maybe 33% have cancer and 23% have heart disease and so on. So you have the same proportions in your sample as in the population in general for that particular research study. Yeah. And of course you need the information to do that. If you haven't got that information beforehand, you can't do that. You might have to kind of use something less accurate, maybe relating to some kind of census data that isn't as accurate as it should be, but good enough for the purpose to do it. The net result is, well, first of all, the stratification factor needs to be relevant to the issue you're dealing with. And again, I think in the example you talked about, it is relevant. Gender, disease, and so on are relevant to anything to do with healthcare. But whatever your study is about, make sure the stratification is relevant. And the most common ones are age and gender, but things like work category, and illness in the case of health studies and so on might be important issues too. Strata should be internally homogeneous and different from other strata. Again, there's no point in using strata where they're all the same anyway. You're trying to bring out the differences in people and trying to reduce those errors that come from those differences. So if they're all the same and homogeneous, it doesn't make any difference. That's the point already. Okay, so there is some extra work involved here in making sure you draw individuals based upon those proportions. You kind of fix the way you're doing it to make sure you get those proportions. The net result, though, is to reduce your sampling error. So your sample is more likely to be representative than otherwise. You're reducing the sampling error. And you can do that disproportionately if you want to. So going back to the example we just discussed, if you have 57% female, 43% male, you might decide that actually we want those proportions proportion in the sample to reflect those proportions and have 57% female, 43% male. Or we might decide actually we're going to have them disproportionately there. We're going to have equal numbers of male and female, but bear that in mind and adjust the figures later. So you can do it either way. You can either draw different numbers, and sometimes you might find you get quite small numbers, just a few people in some subgroups, in which case you might want to increase the number you interview there in you survey rather in your survey disproportionately, and then you have to adjust them later on. You have to reduce their contribution in some sense statistically later on. And that's what disproportionate sampling does. Multistage is where you it does the opposite thing to stratification. Stratification reduces the sampling error, makes it more likely your sample is typical. Multistage does the opposite, makes it more likely it's untypical, but it's done for practical reasons, because it's impractical to do it any other way. It increases geographical concentration, which makes it more convenient, because you can get to people and get to the places, particularly if you're doing it face-to-face interviews in some way. It's very useful, and it's often used in large-scale national surveys where face-to-face interviews are involved, will be done using a multi-stage approach. What you tend to do is divide the sampling frame into large-scale groups. So what have I given here? The counties and towns, the example. So you might say, we're going to do a survey of the whole of Britain. So let's look at, first of all, let's take the counties, and then we'll just select certain counties. Not all of them, but we'll select some, maybe 2 or 3 from the country. And you'll do that at random, of course, using random numbers. So some counties get chosen. And then within those counties, you might say, we're going to choose certain towns or other districts only, and some don't get chosen. So at each stage, you don't need a list of all the people. You need at the first stage just a list of all the counties. At the second stage, you only need a list of the towns and other districts for the counties you've chosen. So it's simpler to get hold of those lists. And then once you've chosen some towns, you might just look at certain streets. And again, you only need a list of the streets for the towns or districts that you've chosen. So it's easy to get hold of those things. You don't ever need a list of all the people in the whole country to do this kind of thing. You can make do with other kinds of sub-lists. So there can be several stages. At each stage you're picking at random, no human choice involved, so it is not a random sample. It does increase the sampling error, and you can do it with probability proportion to size too, and that's often important. If you happen to have chosen in your counties Greater Manchester, that's very big compared with a smaller county like, I don't know, Cornwall or something like that. In which case, the people in Manchester, other things being equal, the people in Manchester are less likely to be chosen. Having chosen Manchester, then picking a subset of people in Manchester, each individual has a lower chance of being chosen. So you can fix that by increasing the proportion in your sample. So you can actually include more people from Manchester because it's a bigger area than Cornwall with a smaller area. And that's sampling with probability proportion to size. Now, can you imagine this is what happens on big, large-scale, professionally done, government-funded surveys. It's a lot of work to do this, but sometimes it's the only way of doing it practically to get out to people. Cluster sampling is where you do that, but the final stage, you just take everybody. So that when you get to a street, you just take everyone on that street, for example. You don't actually sample all the way through. So you don't ever need a sampling frame for the individuals you're actually taking the sample of. So it's a kind of multi-stage approach with the final clusters being taken as a whole and every single individual in that. So it concentrates the sample, as does multi-stage, makes sure that it's practical to go out and contact all these people, and particularly if it's face-to-face, but increases the sampling error as the trade-off. Okay, let me finish with a few words about non-probability sampling. So this is what happens when you don't use random number techniques, probability methods to choose your sample, using some kind of human judgment. And I think probably the most important, the most common approach here is what's called quota sampling. Quota sampling is a stratification approach, so you stratify your sample, but whereas in proper stratification, you still pick people at random, in quota sampling, it's a person choosing them. So you go out and say, I want this number of males, this number of females, I want this number of this age, this number of that age, and so on. And you make sure you fill those quotas, but you fill the quota by choosing people. So there's human choice involved. And you often see this on the street, people with their doing opinion polls on the street, the survey people, will be ticking off, I need another person aged 30 who's male, looking around for a 30-year-old or 30 to 35-year-old male to fill their quota. If you don't fill the quota, then you should, once you ask them their age and check that, if it doesn't come into the quota, you should just simply go on to the next person, ignore them.
Is that how you would get the last, the sampling exercise, the purposive sample of 10 male transvestites?
I don't think so. No, I think that's even more difficult. Yeah, I think that's what comes, I think, into this list here. Oh, let me just do the quota sample, just to go through this again. People chosen by interviewer, so it's not at random. So there's human choice involved, so it's not a random technique. But you are filling quotas, and the quotas can be linked. So you can look for men a certain age and so on, women a certain age, etc. Age and gender are the most important ones that are used here. No sample no estimate of sampling error. But there have been some studies done of this that show that good quota samples, done properly, done well, do give you good samples that are close to what you get by random sampling. So a lot of opinion polls are done this way, commercial opinion polls, because it's quick and easy to do. Last slide, other kinds of non-random sample that you'll come across, particularly in qualitative work. Convenient sample. This is where you basically friends, neighbours, anyone you can get hold of that will answer your questions. And it's obviously going to be biased. It happens who you know. If they know you or they know you're in the friends of friends kind of thing, then it's going to bias it in that way. So it's human choice involved. A version of that, the snowball or the cascade sample, is you start by asking some people and then you ask them for people they know, not necessarily people you know, but other people they know who fit into the category you want, and then the friends of friends of friends and the friends of and so on all the way down. So it's snowballing off from there. And the last kind, purposive, sometimes called theoretical sampling as well, where you're collecting certain kinds of people because your theory suggests it's important to get those differences. I want to make sure I get both people with one leg and people with two legs, because my research shows that one-legged people act quite differently to two-legged people when they're talking about, I don't know, their choice of music. I've just made that up, by the way. But that's the kind of way that theoretical sampling works. It says our theory suggests these differences, so we make sure we get these kinds of people. Purposive sampling, theoretical sampling. These are quite commonly used in qualitative work where it's not even possible to use the random techniques.